Hello everyone, welcome. My name is Derek Boychuk. I'm an offering manager at OPAL-RT Technologies in the automotive sector. And today we're going to be showing you a demonstration on a hybrid powertrain with multiple ECUs in the loop. So just to give a little bit of background, OPAL-RT has been working with NI as a Gold Alliance partner for the past few years now. And our expertise is really when it comes to hardware in the loop simulations, or HIL. And this demonstration is aimed to take NI's great software and hardware and ecosystem and couple it with OPAL-RT's expertise in HIL. And by doing that, we will show you a full hybrid powertrain being simulated on PXI hardware with OPAL-RT software. So what we can see here on the screen is basically connected to my laptop. So this is VeriStand by NI, and it's meant to be the hardware in the loop solution to simulate things such as a hybrid powertrain. So as you can see in this image here on the top left, this shows a block diagram of what we have inside of our simulation. So for example, we have an engine, we have a generator, a charger, of course the converter with the electric motor, and then a battery. So all of these are the plant subsystems that we will be simulating inside of the PXI, and throughout the demonstration I'm going to show you how we can achieve that. Since we're talking about a parallel hybrid powertrain, we do have epicyclic gears at this point connecting both the electric machine with the combustion engine. So when talking about multi-domain or multi-frequency simulation, there's a lot of things to take into account, a lot of challenges. For one, we have a high switching frequency for our converters, our inverter, and we also have electric machine simulating. So to be able to simulate that well and in detail and actually get adequate results, we need to have a very fast simulation time step. So when I'm referring to fast, I mean in the nanosecond time step range. And then for slower aspects like the battery, and other mechanical systems, we can get away with like microsecond or even millisecond simulation. And the beauty of this demonstration is that all of these blocks, although they require different frequencies, we're actually able to do that with VeriStand and with the PXI hardware. So to address these challenges, I'm just going to scroll down here. This is the architecture that we are proposing. So on the left-hand side, we start off with the host computer, which as you can see here is my laptop. This is running Simulink, it's running VeriStand, and this is really what I'm going to use as my workstation to be able to eventually deploy my model. We're connected to a real-time CPU. In this case, it's a PXI chassis, which you see right here. And the PXI chassis, as you know, has many different types of modules for all types of signals and simulation. In our case, what we're really focusing on is the real-time CPU. So the real-time CPU, which you can see right here, is going to be running battery models, some of the control algorithms, etc. And then we also have a CAN card, which is going to be responsible, as you can see by these three CAN buses here, talking with the various ECUs. The star of the show in this demonstration is definitely the FPGA module. So the FPGA module you can see right here. And the FPGA module there is going to be running our solver specifically for power electronics, which is going to be simulating the boost, the inverter, the electric machine, the sensors, etc. And of course, that is then eventually connected to the devices under test. For the devices under test, we're going to move on this side, and we can see that we have a Pi-Innovo ECU, and this is going to be responsible for the supervisory control. And we have an ORION BMS 2 controller as well, and this is going to be responsible for balancing the cells that are emulated with this device from Comemso. So all of this hardware will be explained throughout the demonstration so that we have a better idea of what's being done from the PXI's point of view. So I'll go to the next tab. So here is a high-level overview of what we're going to be simulating. So as you can see here, we have the same block diagram I just showed you previously. So all of these components are going to be simulating inside of the PXI. So inside the PXI right here. And then we have various connections to the different devices. So for example, there's a CAN bus that's going to talk to the Pi-Innovo ECU. There's a CAN bus that's going to talk to the ORION BMS, right, for the battery management system. And then we also are going to have a detailed battery model, like I mentioned here, simulating and sending all of its data to Comemso. And then the Comemso will be able to output voltage and output current so that the BMS can actually balance the cells. So that's an overview of what we're going to be doing. So now it's time to start the demo. So I'll first start by igniting, or by pressing the ignition. So when I press the ignition right now, as you can see, we have two bars here. So there is one for the electric machine, and one for the combustion engine. Because don't forget, we are talking about a hybrid powertrain. So when you first start the car, okay, we expect now the electric machine to be engaged, to be on. And then as we continue on, we can actually play along with the speed and the torque to be able to see at what point, we'll go from the electric machine to a parallel powertrain, and then eventually to a combustion engine, okay, depending on the speed and torque requirements. So all of that decision power, it's actually done by the Pi-Innovo. So the Pi-Innovo has an electric assist control strategy inside of it, so that it will be the one determining whether or not we can go from electric machine power to combustion engine power, and then eventually charge the battery back. Okay? So if I go and increase the speed, and I give it a little bit of torque, okay, we can see here, this tank is basically showing the amount of torque that our electric machine is providing, okay? And we can see that as, for example, we increase the torque, okay, we can see our torque meter going up. And what we'd also notice is that our battery current, which is shown here, is actually going to be draining, of course, more power from the battery pack as our torque increases. So right now, for example, we're at around 30 amps. If I decrease the torque, it's dropping down to about 23 amps. And all of that is coming from, again, the simulated model of the cells. And then at a certain point, for example, if you go at a speed that is too fast for the electric machine to handle, you can see here that we've swapped now between not just electric machine torque, but as well as the combustion engine. So this decision that is basically made because the Pi-Innovo has detected that there is too much speed required for the electric machine to actually produce. So it has switched the powertrain, and now we're having a parallel combustion engine as well as electric machine providing the power. So I'm going to lower the speed again. So now we're stuck basically just with the electric machine. And with this, I will now go to the next tab. This next tab, as you can see, it's really talking about the battery pack. Okay, so the battery pack, like I mentioned before, it's based in Simulink. So we use the SimScape electrical toolbox from Simulink to be able to simulate the dynamics of the battery. And as you can see here, in this demonstration, we have 4 cells. So cells 1, 2, 3, 4. We can see certain things like the state of charge, the voltage output of the cell, the amount of current passing through the cell, etc. That's all listed here. And because we want to actually output this data eventually to the Comemso hardware, we can see that the bottom is actually showing what the Comemso hardware is outputting. So here with the V measure, we can see our 4 cells, and this is the actual measurement of the voltage that's going to be sent out as real voltage. Okay? So this is how the battery pack works. And you can see now that, for example, we're pulling 23 amps away from the pack, and we have a pack voltage of about 194 volts. As I increase, let's say, speed and I increase torque, for example, we can see now that the pack current is going to change accordingly. And what we're going to see later on in this demonstration is once we go from a shared combustion engine and electric machine output, we'll actually be able to recharge the battery if it's requiring or if it's pulling less current than the generator is providing. One last thing to talk about on this page is just the top right corner, as you can see. So this is sort of one of the closed loops that we're doing. So as you can see, it's kind of color-coded. So the battery pack in Simulink, okay, is a sort of pinkish color. So this is simulating the actual battery dynamics. So that's living inside of the PXI chassis, okay? And it's outputting, for example, its voltage and other battery data to the Comemso. So the Comemso BCS right here is going to now input that data and then output a real cell voltage for the 4 cells and eventually connect it to, in this case, this ECU from Orion. Now the Orion, we configure with a standalone tool from Orion, and it's going to be responsible for actually balancing the cells. So if ever there's a cell that's unbalanced, we've programmed it to be able to make sure that all of the cells stay healthy and in the proper voltage. Okay? With this, we have the DC side of the car, okay, taken care of. So the next thing to look at is how do we boost, for example, the 192 volts into something that the inverter wants, okay? This screen shows the boost controller that we've developed. So it's a pretty standard boost control that's happening inside of the PXI. So we don't have the actual controller, in this case external. It's more of a software in the loop approach but if ever you had real hardware that you wanted to connect to, it's just as simple as connecting it to the I/O, and then that way you can have your boost talking to the model that way. So what we can see here is we have a desired voltage output of about 600 volts, okay? And we have a simple PI controller that's going to regulate the voltage to make sure we stay within that 600 range. And of course, if I wanted to, I could change this, for example, from 600 to 650, and we'll see that, oh, that's a little bit high, sorry. Let's put it back to 650, not 6,000. So it might take a little bit of time here to go down. But eventually we come back. So the boost is now regulating the voltage at 650 volts. And you may notice that the line is a little bit jumpy. That is because on purpose we're showing that the gains are not tuned perfectly. We're just trying to show you that there is a little bit of fluctuation, but of course in a real world scenario we would have a much better tuned controller. So we can do other things, for example, like in this case we have a 20 kilohertz switching frequency. We can modify that. We can actually modify the duty cycle to have a manual duty cycle, again for debugging or for optimization. In this current scenario, as normal operation, we can see that our boost duty cycle is about 30%. So I'm going to change this back to the 600. And we can see now we have our regulated voltage at 600 volts. And if I was, for example, to change the torque and other things like that, we can see the boost reacting and trying to maintain that 600 volt range. So now we have the boost, we have our high voltage. So the next step is to, of course, connect that to the drive unit, right? Or to the switching inverter, in this case, the traction inverter. So what we have here is another screen demonstrating what's happening all on the FPGA. So as we're going to see later on, OPAL-RT creates a custom device or an add-on for the NI VeriStand platform that's specifically meant for simulating power electronics and machines. Okay? So as we can see here, we have a circuit which is identical to what's actually simulating on the FPGA with our add-on. And the beauty behind this tool is that even if you wanted to change the circuit or modify something or do anything you want, you can do it on the fly. You regenerate the net list, and there's no regeneration of bit files needed at all. So within a matter of seconds, you can have a completely different circuit, completely open topology to your liking, without having to ever touch FPGA code. Okay? So that's what we offer. If we continue along from left to right, we can see that we had our original battery here, we had the boost, and then we have our DC link, which is about 600 volts. Okay? This 600 volts DC is now going to attach to the inverter, and then the inverter, which is going to be controlled by a field-oriented control, which I'll show you in a few moments, is then connected to the machine, and all of this is happening on the FPGA in the simulation time step of a few hundred nanoseconds. So this is, of course, very important in case where you want to test your machine control or perform certain faults. Now you can do it with an FPGA solution to give you that fidelity that you need. And if you want to be able to parameterize your machine or your inverter, etc., you can do that all with this tool. One thing to show, for example, would be this tab right here. So our tool, like I mentioned, has the ability to have embedded fault injection. So if ever you want to create any type of fault that you can imagine, it's just a matter of putting it in the circuit and then selecting it or automating the process if you prefer. So for example, we can see we have 3 faults right here. We have an inductor that's for the boost, for example, that can fail. We have a capacitor on the DC side here that can fail, and one of the switches, for example, that can fail. This is 3 of among many, many different types of faults you can do. These are just the 3 that we decided to highlight today. So for example, if I click L boost failure here, we can see we have a LED basically saying that this inductance is now shorted together, and we can see, for example, our current has completely spiked up. And this is a fault condition. So for sure it is extremely important to see these types of faults and see how your control algorithm can take them, and this is possible with this tool. I'll go back here to normal operation, okay, and we'll see that the current should come back down right now. And again, these changes are made to the FPGA model without ever having to go inside the FPGA or touch any VHDL code. Okay? Another example is if I want to have the DC capacitor here fail. Well, now we have a capacitor that has completely failed. So we expect our DC link to fluctuate quite a bit, which we can see right here. And if I actually return to the boost control, we can see now that what was once regulated 600 volts is very, very up and down, and it's not regulating it well at all. Okay, so these are again things that you can test to make sure that your boost, for example, can handle such types of faults, and your motor as well. And then another example would be the switch on here, this IGBT right here failing, and again we can see spikes in current and other phenomena. So as I mentioned, these are just 3 examples of among many that we can do. Of course, a very popular one would be to short between phases of the machine, short to ground, etc. This is all possible. It's just a matter of drawing it in the circuit and then activating it. So I will go back to normal operation. Okay, and then we should see our system go back to normal. And there we are. So again, like I mentioned, this is happening all in the FPGA very, very quickly, and it's completely flexible so that if, for example, you don't have a PMSM and you have a squirrel gauge induction machine, we can just swap them out inside the model and you can set all the parameters you want. And these can range in fidelity, so you can have constant or variable inductance tables, you can import from ANSYS or from JMAG. All of that is possible with the same interface that I'm going to show you in a little bit. The next tab is for the control. In this situation, we've opted for a field-oriented control, but any control strategy you want to implement, it's really up to you as a user. We've actually built the FOC inside Simulink, as you can see by this interface, okay, with a few PI controllers. And all of this is actually running in a software-in-the-loop environment. So what I mean by that is we do have, okay, the actual control running inside the real-time controller of the PXI in this situation. But if ever, for example, you want to be able to test your FOC as an external hardware in the loop, it's just a matter of taking this, implanting it, let's say, on your ECU, and then connecting it to the various I/O of the FPGA module. And that's how you can perform a real hardware in the loop with the gate driver or with the motor controller for the drive unit. Okay? If you want to do sensor or sensorless, all of these are possible. Inside of the add-on that I was mentioning before, we do support resolvers, encoders, Hall effect sensors, and we can also have custom sensors inside the FPGA, so to be able to have all control strategies taken care of. And since this is a hybrid demo, I will mention that we do have the combustion engine. In this case, it's not actually part of this demonstration. We would require just a second FPGA module right next to it inside the chassis. In this demonstration, we opted not to show that, but because it is a parallel hybrid powertrain, it's important obviously to mention that we could simulate this. So we do have other videos that we can show, that we can put in the description below, and we will be able to show that you have 2 FPGA modules simulating both the electric machine as well as the combustion engine. And to see some of the signals, for example, that you can have available, we list them right here. And I just want to mention that this is using the engine simulation toolkit from NI, okay, which is, again, a custom device inside VeriStand. So that kind of summarizes the whole demonstration bit by bit. What I'm going to do right now is I'm just going to go back to the first tab right here in the main screen. As I mentioned, this is demonstrating basically the electric machine capabilities. But in the case where you did want to have the combustion engine also be simulated, the controller right now is designed so that it could actually produce the wanted functionality from the combustion engine. So like I mentioned before, if I go, for example, to a torque that's a little bit too much for the electric machine to handle at a certain speed, we can see here that now not just the electric machine is running, but as well as the combustion engine. Okay? So in certain situations, the EACS, right, the electric assist control strategy, has determined that there is simply too much torque for the electric machine, and then we can have the combustion engine turn on and help out. And that's how we can have the parallel simulation. Now in cases where we're going simply too fast, okay, such as here, we can see, let's say this is in kilometers per hour, not miles an hour, okay, which is still got to stay within the speed limit. Now we have the full combustion engine producing the output. There's zero output from the eyes of the electric machine. As we can see here, we actually have a negative battery current, which means that the a combustion engine is producing power with the generator, that it's actually charging the battery. So we can see here that the battery state of charge is going up, okay, by 0.01%. This can, of course, be modified. In our situation, it's a demonstration, so we tried to show a little bit sped up. But of course, if you want to have a more realistic battery model, we can just insert the battery model there. If I now go back to the battery pack tab, we can actually see that since we're charging, okay, our Pi-Innovo, our ORION device, our BMS, we've programmed it to actually start balancing cells that are unbalanced. And that's what we can see right here. So again, we have our 4 cells, okay, each with a different state of charge and different voltage. And we can see here that the state of charge of the 4th cell is 77%. And we've programmed it so that when it's within a certain range or outside of that certain range, we want to start balancing that cell to be more in line with the rest of the cells. So this is one other application of why it's so important to have the cell emulator from Comemso as well as the ECU from ORION to be able to test not only the hybrid powertrain, but as well as optimizing the BMS control of the system. So with that being said, I will go back and turn the torque a little bit lower and the speed as well. So now we've gone back again to the electric machine. The electric machine is now pulling a positive amount of current, so it's discharging the battery. And now we can let this run basically to be able to see if our state of charge will go down and have our BMS control when it's time to charge and not deplete the battery completely. So another cool feature of VeriStand is the ability to actually visualize all the signals that we have here. So if I go to the first tab, which I haven't shown you yet, okay, this it might look a little bit confusing at first, but this is something that we draw up to show everything and all the different loops that are happening in our simulation. So if we start on the left-hand side, we have certain signals, okay, and certain inputs into the simulation, okay? And then as we kind of move forward or move to the right, we can see different aspects. So for example, we have the ECU. So the Pi-Innovo device, right, that's the supervisory control. It has certain inputs like the battery state of charge, the ignition, etc. And all of this is going to be part of the decision power that it's going to need to either activate the combustion engine or the electric machine, etc. We have the FOC control, right? So to be able to actually control the electrical machine, we can see it's here. And again, this is a software-in-the-loop approach like I mentioned before, but there's nothing stopping us from taking this model, deploying it on real hardware, and then having a hardware-in-the-loop situation. This is connected to the power electronics add-on. The power electronics add-on is what we talked about before from OPAL-RT. It is the custom device meant to simulate the power electronics of the vehicle as well as the machine. And this is one closed loop, as we can see right here, between the plant model being the inverter and the traction drive with the field-oriented control. And last but not least, we have the battery model. So the battery model is, like I mentioned, a Simulink model using the SimScape toolbox from the Mathworks. And it is simulating in the real-time controller a very detailed battery model to then connect to the Comemso hardware, and then from the Comemso hardware, that's connected to the ORION, and the ORION will perform the cell balancing that we saw before. And that's another loop. So this is an idea to give you an overview of what is being simulated, what's talking to what, and hopefully that clarifies a little bit of what I was trying to demonstrate today. The last thing I'd like to show you is the system definition file of VeriStand. So if I open up my system definition file right here, okay, for those of you who don't know, this is what it would look like when you open up the demonstration. So what you see right here is the system definition Explorer window of NI VeriStand. And on the left-hand side, we have various parts that we have to actually talk to the model, import models, and configure the whole system. So in other words, this is the main configurator panel that allows us to make sure that all the parts can talk to one another. So as I expand my left-hand tree here, we can see that under custom devices, there are two custom devices. The first one is the engine simulation toolkit from NI. So that's meant to simulate the engine. You can take real engine data, import it, send it as an analog channel, etc. It's a very robust tool. And what OPAL-RT specifically designs is the power electronics add-on. So in the power electronics add-on, okay, we have the ability here to create a circuit, in this case based in SimScape, that will simulate the inverter, the boost, the machine, etc. And you have certain things such as the number of scenarios you can use. This is where you define your scenarios. And you can see that it requires a time step of, in this case, only 210 nanoseconds, which is extremely, extremely fast. As we continue down the tree, we can see that this bit file, this firmware, supports a dual PMSM machine setup. In our demonstration, we were only using one, but there's nothing stopping us from using two. And as you can see, we have different motor configuration types. So if you want constant LDLQ, if you want variable LDLQ, if you want to simulate a BLDC, we can all do that from this window. And we can also support, for example, spatial harmonics models for PMSM models, where you can import, like I mentioned before, 3D tables from ANSYS, from JMAG, and from other finite element analysis tools. The last thing that I'd like to show you is this part, because it's extremely important for this demonstration, is the simulation models. So under simulation models, you can see here we have 4 different models. There's the battery model, there's the boost controller, the FOC, and we have actually a function for a torque ramp. So these are 4 models that we've developed outside of VeriStand in Simulink, and we've then compiled them to a Linux executable file that we then import into this model, and this is how we can map that actual battery model connected eventually to the rest of this system. So without going into too much detail, I think that's the summary I want to give on how we configured this whole demonstration we just saw using the VeriStand tool. I hope it was helpful. And for any questions, please contact OPAL-RT, and we'd like to thank you for taking the time to watch this demonstration today.